Let R be a relation defined on the set of natural numbers n as R is a set containing the ordered pair x, y such that x is a natural number, y is also a natural number, and we have a relationship between x and y given by the equation 2x plus y equals to 41. We need to determine the domain and range of this relation R and also verify whether R is reflexive, symmetric, and transitive. Okay, let us begin. So here we have a relation R which is defined on the set of natural number. And defined on the set of natural number simply means that R must be a subset of the Cartesian product of the set of natural number n with itself. And here how we are defining R, it is defined as the set containing the ordered pairs x, y such that x and y are both natural numbers, and then the relationship between x and y is such that we have 2x plus y equals to 41. Now, taking the help of this equation 2x plus y equals to 41, where x and y are natural numbers, we're going to form the set R consisting of the ordered pairs x, y. Okay, so here we have the equation 2x plus y equals to 41. Okay, so let's isolate y from here. So isolating y is going to give us 41 minus 2x. Now we're going to take some specific values of x. So x is going to be some natural number such that y is also a natural number. So if we consider x to be equals to 1, then the corresponding y value is going to be equals to 39. Okay, so let's find out the values of x and y here. So that means if we take x to be equals to 1, then corresponding y value will be 39. If we take x equals to 2, the corresponding y value will be 37. So we continue this all the way up to the last value for x, which is going to be 20. Then in that case, y is going to be 1. We'll not be taking any values greater than 20 for x. Then in that case, y becomes negative, and that's not possible since it's already mentioned here that y must be a natural number. So here, using this table, we can now form the ordered pair for the relation R. So R is going to be containing the ordered pair 1, 39. Next we have 2, 37, and this is going to continue all the way up to the last ordered pair, that's 20, 1. Fine. So this is our relation R. Our goal will be to find out the domain and range of this relation. So what is the domain of the relation R? That's a very simple task. To find out the domain, we only have to consider the first element in each of the ordered pairs. Now the first element that corresponds to all the values of x. So that means here we have 1, 2, 3 going all the way up to the last value of x, that's 20. So there are a total of 20 elements that belong to the set, the domain of R. And then we will find out the range of the relation R as well. So the range is going to be defined as the elements that occur in the second position of each of the ordered pairs. So we have 39, 37, and that means the corresponding y values, 37, then we have 35 going all the way up to 1. So that's going to be the range of the relation R. So now that we have obtained the domain and range, let's go to the next part of the problem. We need to verify whether R is reflexive, symmetric, and transitive. Okay, so let's first check for reflexivity. So for this, what we'll do, we're going to consider an arbitrary element. So let x be an arbitrary element such that we have the equation 2x plus y equals to 41, but what we'll do, we'll replace the y with x. So that gives us 2x plus x equals to 41. So we get 3x equals to 41, and that gives us x equals to 41 over 3. And clearly this is not a natural number, so it does not belong to the set of natural number, which means that we can say that R is not reflexive. R is not going to be a reflexive relation, because what is the criterion for any relation to be reflexive? The only criterion is that R is reflexive. R is going to be reflexive if and only if we have the element a, a belonging to the relation R for all values of a belonging to some set A, the set A on which the relation R is defined. So in our case, we should have obtained is that for all values of x belonging to the set of natural number x, x should have belonged to the relation R. Only in that case we could have said that R is reflexive, but since we are getting x to be 41 over 3, so here it's not going to be reflexive. Okay, so the first one is done. Let's check for symmetry. Now to check for symmetry, we're going to consider the ordered pair x, y belonging to the relation R. Now, what does it imply? This simply implies that we have 2x plus y equals to 41. Now, from the definition of symmetry, the definition of symmetry says that if we have an ordered pair A comma B belonging to some relation R, then it must imply that B comma A belongs to the relation and R. Then only we can say that R is symmetric. R is symmetric. Now in our case, what we have here, we started out by considering an ordered pair x comma y belonging to the relation R, and we know that this simply is related by the equation, x and y is related by the equation 2x plus y equals to 41. Now if we are to show that y comma x belongs to R, then only we can say that R is symmetric. Now for y comma x to belong to R, in order to show y comma x belonging to R, we need to show that 2y plus x equals to 41. Now is there any way can we rearrange the terms in this equation to make it look like 2y plus x equals to 41? No matter whichever way we try, we can never do that. So here 2x can be broken down to rewrite this as x plus x, and y can be rewritten as 2y minus y equals to 41. Now this is going to give us 2y plus x. So we are going to transpose 1x and negative y to the right hand side to get 41 minus x plus y. Now this is no way matching with this particular equation, 2y plus x equals to 41. This simply tells us that y comma x cannot belong to the relation R. So this could be best understood with the help of an example. So here we have already verified that 1 comma 39 clearly belongs to the relation R, but 39 comma 1 does not belong to the relation R. We have already verified it while considering the ordered pair for R. So 1 comma 39 belongs to R, but 39 comma 1 does not belong to the relation R. So this simply means that our relation R cannot be symmetric. So this is not symmetric. Okay, so we have verified that our given relation R is not symmetric. Now let's go to the third one. Now in the third case, we have to check whether if R is transitive. So we have to check for transitivity. Okay, so what is the meaning of transitivity? When we say that a given relation is transitive, that means if we have the ordered pair A comma B belonging to a relation R, and we have another ordered pair B comma C belonging to the same relation R, then it must be true that A comma C must belong to that relation R. In that case, we say that R is transitive. Now the way we choose the two ordered pairs at the beginning, that's very important. So here the second element of the first ordered pair must be exactly the same as the first element of the second ordered pair. So here in our case we have B, so that means the remaining elements, so that means the first element of the first ordered pair and the second element of the second ordered pair, they must combine together to form a new ordered pair A comma C, and it must also belong to that same relation R. Only then we can say that R is transitive in nature. So here let's do one thing. So let us suppose that let x comma y belongs to the relation R, and we are going to consider another ordered pair y comma z also belonging to the relation R. Fine. So what is x comma y belonging to R? This simply means that we have the equation 2x plus y equals to 41. So x comma y belonging to R simply means 2x plus y equals to 41. And we have the ordered pair y comma z belonging to R. This is simply going to give us the equation 2i plus z equals to 41. All we have done is substitute the value of x with y and substitute the value of y with z. So here we are getting two equations. We're going to combine these two equations. So here let's do one thing. Let's isolate y from here. From y, because we need to get rid of y. So y is going to be equals to 41 minus 2x. So let's substitute this y back into this equation such that we get 2 times 41 minus 2x added to z equals to 41. So we get 84 minus 4x plus z equals to 41. So when we rearrange the terms, we're going to get 4x minus z equals to, so we have 43. Now clearly this is not an equation. What our actual equation should have been, if we assume that R is actually transitive, then we should have gotten, according to definition, what we should have gotten. We should have gotten x comma z belonging to the relation R, which simply means that our equation should have of the form 2x plus z equals to 41. But what we are getting here, we are getting 4x minus z equals to 43. This clearly tells us that the ordered pair x comma z cannot belong to the relation R. This is simply telling us that. In other words, here we have shown that R is not transitive as well. R is not transitive. Fine. A given relation is only going to be reflexive. It's not going to be symmetric, nor it's going to be transitive. Okay, fine. So that means we have finally solved our problem. Let's go to the problem again. So here we have our relation R defined on the set of natural numbers. The R is defined here. So we obtain its domain and range. The domain is given and we also obtain its range. And then we were able to verify that it is only reflexive. It is neither symmetric nor transitive.